Okay, welcome students back. We're going to cover 1.8 now. So let's get into 1.8 here. Okay, 1.8 is on change of variables. Definition. A function is said to be homogeneous of degree 0 if f of tx ty is equal to f of xy. Okay, so I put a constant on t and a constant on y. Okay, this t variable, okay, on xy, is that equal to the function of xy? Are they the same? Okay, for all positive values of t. For which tx, ty are in the domain of f. Okay, let's do an example of this. Okay, show that f of xy equals x squared plus 3xy minus y squared all over x squared plus 4y squared is homogeneous of degree 0. Okay, so is it linearly homogeneous? Okay, so f of tx ty would be equal to tx squared plus 3 tx ty minus ty squared all over tx squared plus 4 ty squared. Okay, so I'm going to get some t squared x squared plus 3t squared xy minus t squared y squared all over t squared x squared plus 4t squared y squared on the bottom. And what I want to do now is factor out the t squared on top and factor out the t squared on the bottom. And I get x squared plus 3xy minus y squared all over x squared plus 4y squared. And the t squareds will cancel out, and so that does equal my original function, f of xy, and so therefore it is homogeneous. Okay. Okay. If we look at the original equation, f of xy, and we factor out an x squared, so let's look at that real quick. Okay. So the original equation was x squared plus 3xy minus y squared over x squared plus 4y squared. I'm going to factor out an x squared here on the top. factor out an x squared on the bottom, I get 1 plus 3 over x, or 3y over x, right? Because I would factor out an x squared, I'd have to create, well, let me write it like this. 3y over x. Okay, so again, if I pull that x squared back in, I should just get 1x, right? Because the x squared and the x will cancel, leaving me with 1x. Okay, nice. Now this doesn't have an x squared. So if I make it x squared over x squared and I pull out the x squared on top, it should just leave me with that x squared on the bottom. So this will be y squared over x squared. Okay, all over. Pull out an x squared on the bottom, I'm left with 1. Plus, this is 4 y squared over x squared. Okay, let's cancel that x squared out. This is going to be equal to 1 plus 3 times y over x minus y over x squared, all over 1 plus 4 times y over x squared. Okay, now if we replace this y over x with another variable, if we say let v equal y over x, then we could think of this as a single variable. Okay, so this could be 1 plus 3v minus v squared all over 1 plus 4v squared. So that's kind of the substitution that we're going to be using, okay, to solve some differential equations. Because I know that if I can rewrite it in terms of y over x, that it is homogeneous. Okay, and then I can just kind of sub out the v equals y over x, okay, and sub in v as a dummy variable, and then reconcile that at the very end. Okay, I shouldn't say dummy variable, there are no dummy variables. I should say maybe substitutive variable. Okay, theorem. A function f of x, y is homogeneous of degree 0 if and only if, okay, if and only if it depends, this IFF is just shorthand for if and only if it depends on y over x only. Okay, so if I can turn it into y over x as the single, it's a single variable, then it is homogeneous. Okay, a definition. Okay, if f of x, y is homogeneous of degree 0, then the differential equation dy dx is equal to f of x, y, is called a homogeneous first order differential equation. So if we get dy dx equaling some homogeneous function, then it is called a homogeneous first order differential equation. Okay. Now, let's think of v in terms of y over x. Okay, v is equal to y over x. So I'm going to multiply both sides of this equation by x. And so I would get y equals vx. But v really is kind of a function of x. So I'm going to rewrite this as y equals v of x times x. Okay, so if we get y equal v of x times x, okay, then what would the derivative of that be? What would dy dx equal? Well, dy dx is going to equal, well, let's do the chain rule here, okay? I mean the product rule, okay? Derivative of the second times the first, well, that's just v of x. Okay. Okay, and then derivative of the first, well, that's dv dx times the second, which is x. Okay, and I'm going to get rid of the v of x. I can just place that back to v, just as long as we know that that's a function of x. V is a function of x. Okay, so dy dx is equal to v plus dv dx x. Okay. So we have this equation, this equality here. Okay, we let v equal y over x, and if y over x is my sole variable in the whole thing, then I know it's homogeneous first order differential equation if dy dx equals this thing. Okay, and so we could say that dy dx is going to be equal to some f of xy. Okay. Okay, some homogeneous first order differential equation there. Okay, then what we can do here is we could say, well, this is v plus the dy dx is v plus dv dx times x. Okay, so we're setting up this substitution, this equation, this equality, so that we can do this substitution. Okay, is equal to, and I'm going to say that this is f of v, where v is equal to y over x. Okay, and so I'm going to subtract v on both sides. I get dv dx x times x is equal to f of v minus v. Okay. Okay, and so we now can end up with a separable differential equation. This becomes separable in that I could divide by the f of v minus v, and then divide by the x and multiply by the d of x. So let me just show you what that looks like. This would be 1 over f of v minus v times dv. is equal to 1 over x dx. Okay, so I just divided by x, multiplied by dx, basically got that guy to the other side. Reciprocal of x dx, got this guy here, x dx, right? Took the reciprocal of that and forced them on the other side. And then f of v minus v, okay, that I'm going to do the reciprocal as well. Okay, and that's 1 over f of v and f of v minus v dv. Okay, thus, it becomes a separable differential equation. So we took something that was a little bit more complicated and turned it into a separable differential equation as long as it's homogeneous. Okay. Okay, so let's just kind of jump right in and see what we're talking about here. Okay, so number 2. Find the general solution to the differential equation dy dx is equal to 4x plus y over x minus 4y. Okay. Okay. So the first thing we want to do is check for homogeneity. Check if this thing is a homogeneous differential equation. Okay. So let's check for that. So t of x, ty, does that equal f of xy? Okay, so I plug in these t's. Does that work? Okay, so that's one way to check for homogeneity. Okay, the other would be to factor out an x. Okay, we can check it that way as well. Maybe we'll do both ways. But what does f of t of x, t of y look like? Okay, well, it looks like 4 times t of x plus t of y all over x minus 4, oops, t of x minus 4 ty. Okay, tx minus 4 ty. Okay, and I'm just going to factor out the t. Okay, so this is t times 4x plus y over t times x minus 4y. T's cancel, and I'm left with f of xy. So yes, that works. The other thing that we can see here is if I take dy dx and I factor out an x on the top and bottom, okay, I would be left with 4 plus y over x over 1 minus 4 y over x. And so the single variable here in quotation marks is just y over x. Okay, and so if this function only depends, f of xy only depends on y over x. Okay, that's the only variable that we're dealing with. All right, so we know it's homogeneous at this point, so we're pretty convinced of that. So now let's use a substitution, okay, to get something that looks kind of hard to integrate. It's not separable, and turn it into something that is separable. Dy dx is equal to 4x plus y over x minus, oops, x minus 4y. Okay. Okay, so let's let v equal y over x, or more importantly, let's let let's let y equal vx. Okay, let's see what happens here. Okay, so we get dy dx is equal to 4x plus vx over x minus 4 times vx. Okay. Okay, this becomes dy dx is equal to okay, dy dx is equal to pull out the x, 4 plus v over x times 1 minus 4v. Okay, so we've got dy dx is equal to 4 plus v over 1 minus 4v. Okay, so how does that help me? We need to get things in terms of v now. Okay. Remember v is v of x. Okay, v is a function of x. So this really is y equals v of x times x. And I want to find dy dx. I want to find the first derivative of this. And what is that equal to? This is equal to the dy dx over here, but I want to know what is that dy dx represent if this originally was my substitution that I'm making. If I'm plugging in this variable v, how does that affect my derivative? Well, once again, that's going to be the product rule. Okay, derivative of the second times the first, okay, is going to be v of x times 1 plus derivative of the first, which is v prime, or dv dx, times the second, which is x. So this is just v times 1. So dy dx is equal to v plus dv dx times x. And that, my friends, is going to go there. Okay, so v plus dv dx times x is equal to 4 plus v over 1 minus 4v. Okay, because we really want dv dx. We don't want dy dx because we're not using y anymore. We're using v as our variable. So it doesn't do us much good to have a dy dx. We need a dv dx. Okay, so I'm going to subtract the v here. I get dv dx times x is equal to, and I'm going to create a common denominator. Okay, this is going to be 4 plus v over 1 minus 4v minus v times 1 minus 4v over 1 minus 4v. Okay, you get dv dx times x is equal to okay, distribute the top. Okay, and I get 4 plus v minus v plus 4v squared all over 1 minus 4v. Okay. Okay, so dv dx x is equal to 4 plus 4v squared over 1 minus 4v. Okay, okay, good, 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 good. Okay, so now we're gonna create a separable differential equation. Okay, so we're gonna multiply by the reciprocals here. And I'm going to get 1 minus 4v over 4 plus 4v squared. Okay, dv is equal to 1 over x dx. Okay, so just taking the reciprocals and separating out the variables. Okay. Okay, so I'm going to split this. I'm going to try to integrate now, but I'm actually going to split the left side into two different integrals. I'm going to go integral of 1 over 4, maybe I'll factor out that 4, 1 plus v squared minus 4v over 4 times 1 plus v squared. So those 4's are going to cancel. Okay, just break it up into two terms, and then I'll integrate each of those terms individually. Okay, is equal to the integral of 1 over x dx. Okay, so this, let's break it up into two integrals. This is 1/4 times 1 over 1 plus v squared minus the integral of v over 1 plus v squared dv. Okay, and that equals the integral of 1 over x dx. Okay, so we've got three integrals here that we need to integrate. Okay, the first one, if you remember back to calculus class, this is the arctangent. So this is 1/4 the arctangent of v. Okay. The second one here, this, because I have a v up top and I have a 1 plus v squared on bottom, this is just a u sub. Okay, so u is equal to 1 plus v squared, du is equal to 2v dv. There's my v dv right there. And so I just need to divide by 2. Okay, and so this is minus the integral of 1 over u du over 2. Okay, so this just becomes minus the integral of 1 over u is just natural log. So this is going to be 1/2 natural log of u. Okay, and so, but what was u? U was 1 plus v squared. Okay, and so we have our 1/4 arctangent v minus 1/2 natural log of absolute value of 1 plus v squared. Okay, is equal to, what's the integral of 1 over x dx? Yeah, that's just natural log of x. So natural log of the absolute value of x, and then let's add on our plus c. Okay, I'm going to call that plus c1 because that c is going to change in a second. Okay. So now what do we want to do? Well, we kind of have this solved, but I'd really like to simplify it more. And I'd like to go back to my original variables. Okay, so what I'm going to do is I'm going to say, well, v was equal to x over y. Okay, and so we have 1/4 of the arctangent tangent of, oops, this was, sorry, y over x. Okay, y over x. Okay, minus 1/2 times the natural log of, natural log of 1 plus y squared over x squared, y over x, but we won't skip steps. Y over x squared is equal to natural log of x plus c1. Okay, that looks good, but we can do a little bit better here. Okay, on simplifying this. I'd like to multiply both sides by 2. Okay, Okay, because that's going to allow me to combine some natural logs here. Okay, so if I get rid of this negative 1/2, then I can combine some natural logs. It would be maybe a little nicer in the end. So let's do that. Okay, I would be willing to accept this line as an answer, like on an exam. I'm just cleaning up the algebra at this point. Okay, so I wouldn't necessarily require you to do the next steps. Okay, I'm going to multiply both sides by 2. Okay, and what I get is 1/2 arctan of y over x minus the natural log of 1 plus y squared over x squared. Okay, is equal to 2 natural log of the absolute value of x plus 2c1. Okay. Okay, now I'm gonna toss this guy to the other side. Okay, so he becomes the next line is 1/2 arctangent of y over x minus natural log of, okay, I'm going to create a common denominator here, x squared over x squared plus y squared over x squared minus 2 natural log of x is equal to 2c1, and next line I'm going to call that c2, okay, or just c at the very end, because that will be my constant. Okay, so now we have 1/2 arctangent of y over x minus the natural log, okay, of x squared plus y squared over x squared, okay, minus, and I'm going to make this 2 be the exponent. So we've got 2 times the natural log of the absolute value of x squared is equal to, I'll call that c2. Okay, where 2c1 is equal to c2. Okay, now what we're going to do is we are going to try to combine these natural logs. Okay, maybe I'll do an extra line here just to convince you of what I'm doing algebraically. X arctan y over x minus, this is, I'm going to factor out the negative, okay, from this. Okay, and this will become natural log of x squared plus y squared over x squared, okay, plus, okay, the natural log of, and I can bring this squared inside, right? If I absolute value x, that's positive. If I square it, it's positive. So I could bring this, regardless of what I do, I can bring that x squared in the absolute value bars. It's not going to change the result because it's going to force everything to be positive anyway. Okay, and that equals C2. Okay, so 1/2 arctan y over x minus, okay, the natural log, okay, the sum of natural logs is the product of their values. Okay, natural log of x squared plus y squared over x squared times x squared. And lo and behold, those x squareds cancel out. That's why I did this whole thing. We'll see 2. Okay, and so we left with 1/2 arctan y over x minus the natural log of x squared plus y squared equals C2, or we'll just call that C. And that's about as far as I want to go with that. Okay. Okay, let's look at another substitution. Okay, so that was a substitution for if they're homogeneous. Okay, now we want to look at something called a Bernoulli equation. There are a lot of famous Bernoullis in math around the 1600s. Okay, I don't know which Bernoulli this one is named after, but lots of Bernoullis. They were a famous mathematical family in Italy. And, kind of in the 1600s, it was, the kings of all of the countries. It was very chic, and it was a kind of a, you were the height of society if the king, um, king wanted to look smart, he had really smart people around him. So you had all of these mathematicians in the 1600s, they just go work for the king, and he'd be like, oh yeah, those are my mathematicians. Those are all my smart guys. And the Bernoulli family, they were a ton of smart guys, and uh, the whole family, well, basically worked for the king of Italy. And yeah, came up with the natural exponent. One of them did. He was a financial mathematician and came up with compound interest. So you can thank the Bernoulli family for compound interest. Okay, but this is called the Bernoulli equation in differential equations. Okay, a differential equation that can be written in the form of dy dx plus p of xy equals q of x. This almost looks like a first order linear differential equation until we see that this is y to the nth power on the end. So we end up with this kind of weird, y to the nth power, on the end here. And that kind of messes things up. So we have to do a special substitution to help us turn this into a linear differential. It's almost a linear differential equation, but we just have to do a special substitution to turn it into one. Okay, a differential equation that can be written in this form. Okay, where n is a real constant. Okay, is called a Bernoulli equation. Bernoulli equation. Okay. For a Bernoulli equation, multiply through by y to the negative n, okay, and use a change of variable u of x is equal to y to the negative n plus 1. Okay, okay, that would make du dx equal to negative n plus 1 y to the negative n plus 1 minus 1, which is just negative n. Negative n, it would be plus 1, and then minus 1. Right? We took the derivative of that. Just bring the exponent down and then subtract 1. But we already have a plus 1. And that's why we use that substitution, and then it becomes y to the negative n. Okay, but y is a function of x. So don't forget that there's a y prime. We need to do some implicit differentiation there. So that's a dy dx. Okay. So if we were to divide both sides by negative n plus 1, okay, we would get y to the negative n dy dx is equal to 1 over negative n plus 1 du dx. Okay, so this is going to come in very handy when we have to go from dy dx to du dx. Okay. Okay, so solve. Let's solve this Bernoulli equation. Solve dy dx plus 3 over x y is equal to 27 y to the 1/3 times natural log of x. Okay, so we have kind of p of x here, and we have kind of q of x with 27 and natural log of x, but we've got this y to the 1/3 kind of gumming up the works. Okay, so what do we need to do? Well, we need to multiply both sides by y to the negative 1/3. Okay, let's do that. Okay, so we've got y to the negative 1/3 times dy dx, okay, plus 3 over x y equals 27 times y to the 1/3 natural log of x times y to the negative 1/3. So those are always going to cancel each other out. That's why we do this. And we could distribute, that's y to the negative 1/3, distribute that, and we get y to the negative 1/3 dy dx plus 3 over x, this is y to the first times y to the negative 1/3, is equal to 27 times the natural log of x. Okay, I put the y to the first side because we're just going to go y to the first minus 1 minus 1/3. That's going to be y to the 2/3. Okay, so y to the negative 1/3 dy dx, okay, plus 3 over x, y to the 2/3 is equal to 27 natural log of x. Okay, nice. Okay, so let's let u be equal to, what? What do we want u to be equal to? Let's go back up here. U equal to negative n plus 1. Okay, and what was our original that we multiplied through? We want to multiply through by y to the negative n. Okay, so negative n plus 1. So we want u to be equal to y to the negative n plus 1. The negative n refers to the exponent negative 1/3 that we initially multiplied y to the negative 1/3 through. Okay, so that's going to be y to the negative 1/3 plus 1. And so u is equal to y to the 2/3. Okay, so that's interesting because that's exactly what I have here. That was kind of the goal. The goal is I wanted to get u to be this over here. Okay, and we'll see why that's important in a second. Okay, so then let's take the derivative. Du dx is equal to then 2/3 y to the negative 1/3 dy dx. Okay, well, yes, I like that because look here, I have a, if it will come up for me. Okay, I'll just put it in red. I have a y to the 1/3 dy dx. And I just have this 2/3 over here kind of gumming up the works. So what I'm going to do is multiply by the reciprocal, 3/2. And I can say, look, this thing over here, I can replace with 3/2 du dx. I don't have to deal with a y to the -1/3 anymore. That's awesome. I also don't have to deal with a y to the 2/3 because that just became u. So this becomes a linear differential equation really quickly. This becomes 3/2 du dx plus 3/x u. That's what 2/3 was u there. Okay, and then that equals 27 natural log of x. That doesn't have any y's or u's, and so I'm good. Okay, this just became a linear differential equation. Oh, nice. Okay, I could multiply through by 2/3 if I really wanted to. Okay, so that's going to become du dx plus 2/u, or 2/x, right? So this is, I'll just multiply it out. This is 2/3 times 3/x. Okay, u, 3's are going to cancel, is equal to 27 times 2 is 54, divided by 3 is 18. So that's 18 natural log of x. So this becomes du dx plus 2/x u is equal to 18 natural log of x. Okay. So now this is just a linear differential equation in terms of u. Okay, no longer is in terms of y. It's in terms of u. So let's solve the linear differential equation just the way that we know how to do that. So that is going to be, take my I of x, that's e, find my integration factor here, e to the p of x dx, which is e to the 2/x, okay, dx. So this is going to be equal to e to the 2 times integral 1/x dx, which is e to the 2 natural log of absolute value of x. I'm going to put that 2 and make that my exponent. So this is e to the natural log of x squared. Okay, that just become x squared, and the e to the natural log cancels. Okay, and so we just get x squared. So that's what we're going to multiply through by to solve this differential equation. Okay, so we're going to go x squared times du dx plus 2/x u is equal to 18 natural log x times x squared. Okay, so this is going to become x squared du dx. Okay, distribute that. Distribute, and I get 2x u is equal to 18x squared ln x. Okay. Okay, it's looking good. We can product rule this guy. Okay, product rule that guy by saying d dx of x squared u, right? Because if I take the derivative of u, I get du dx. If I take the derivative of x squared, I get 2x. So there we go. Okay, is equal to 18x squared ln of x. So now I'm just going to integrate both sides. And the integral and the derivative are going to cancel. This is x squared u is equal to, this is going to be integration by parts. Okay, so u is equal to, I can pull the 18 out in front if I want to. It doesn't really matter. I'll just let it be 18x squared. The dv is, no, I don't want that. I want the natural log first. Okay, the natural log, and then we'll do 18 for dv. We'll do 18x squared, because when I cube that, I can divide by 3. And if I integrate that, that becomes 6x cubed. That's nice. And then the natural log du is equal to 1 over x dx. Okay, so now v du, okay, this is equal to 6x cubed natural log x minus the integral of, I don't have to deal with the natural log anymore. That's great. 6x cubed times 1 over x dx. Okay, that's cool. That just becomes 6x squared because one of the x's are going to cancel. So that's 6x cubed natural log of x minus integral of 6x squared dx. Well, that's x squared u. Okay, and that is equal to x squared u, 6x cubed natural log x minus the integrate that, that's going to become a third power divided by 3. That's 2x cubed plus c. Okay. Nice, nice, nice. Okay. And so just divide by x squared. Divide everything by x squared. And we get u is equal to 6x natural log x minus 2x, okay, plus c over x squared. Okay. Maybe I'll factor out this 2x here. 2x times 3 natural log x minus 1 plus c over x squared is equal to u. But our original function wasn't in terms of u. So we're just going to plug back what u was. What was u? Let's go back up here and see. What was u? What did we define u as? Well, we defined u as this guy here. Okay, u is equal to 2 y to the 2/3. And so, yeah, that's exactly what y u is. It's y to the 2/3 is equal to 2x times 3 natural log x minus 1 plus c over x squared. And we could take this to the 3 power both sides and solve for y, but it's fine to just leave it like this. Okay. Okay, that that was 1.8, and I will see you in the next section.